Let us look at polynomial-exponential series. Let the general term of the series be f of n by n factorial, where f of n is a polynomial in n of degree m. Rewriting the polynomial in falling factorial form, we get something like this. F of n is equal to a sub naught plus a sub 1 times n plus a sub 2 times n minus 1, and so on up to the mth term. Now let's substitute the falling factorial form into the general term of the series. So series n equal to 0 to infinity of f of n divided by n factorial is equal to the series with the falling factorial form of the polynomial divided by n factorial. Let's split them up into component sums. We get the series a sub naught divided by n factorial, the series a sub 1 times n divided by n factorial. Similarly, series a sub 3 times n minus 1 times n minus 2 divided by n factorial, dot, 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 dot. So that finally we have the series a sub m times n minus 1 times n minus 2 dot, 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 n minus m plus 1 divided by n factorial. Simplifying this, let's take the constants or the coefficients out of the summation. We get this expression. And now, in the second term, you have n by n factorial. So this n factorial in the denominator can be written as n times n minus 1 factorial. That means n and n cancel out, and we are left with 1 by n minus 1 factorial. Similarly for the rest of the terms. So this will become 1 by n minus 2 factorial. And finally, the mth term will become a sub m times the series 1 by n minus m factorial. Now here you have to be careful about the starting point of the index. So it starts with n equal to 0 here. For this, n is equal to 1. Why? Because if we say n equal to 0, what happens? We end up with a negative factorial. Now, since f of n is a polynomial of degree m, it contains only finitely many terms. Further, each component series is of the form 1 by n factorial, albeit with shifted indices, and therefore absolutely convergent. So each of these series are absolutely convergent. So the linear combination of absolutely convergent series is convergent. Therefore, splitting the sum as above into separate sums is valid. So this was the justification for splitting this sum into this individual sums. Now, here if you notice, this is equal to E. And here, this series is just a shifted, or rather the tail series corresponding to the first series. This is again a series which is a tail series of this series. So since all the series except the first one is the tail series of the first series, that means they are all convergent and they converge to the same quantity E. So we have a sub naught times E plus a1 times E plus a2 times E plus dot 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 plus a sub m times E. Now taking common E out, we end up with the series f of n divided by n factorial is equal to E times the series, rather a finite series of a sub k. This result is for any polynomial expressed in falling factorial form. we have arrived at an identity. So if we are given a series in this form, immediately we can take the product of E with the summation of the coefficients A sub k, where k goes from 0 to m. So interestingly, the sum reduces to the value of the polynomial at n equal to 1. Since upon evaluation, all terms except those containing a sub naught and a sub 1 become 0. So here, if you notice, if we look at this, when n equal to 1, what happens? N minus 1 minus 1, this becomes 0. That means the whole thing becomes 0. This becomes 0. And all the in-between terms also become 0. What doesn't become 0 is this. This also doesn't become 0. So which implies that the series f of n by n factorial is equal to e times a sub naught plus a1, which is nothing but e times f of 1. Let's write it as a theorem. If f of n is a polynomial in n of degree m and written in following factorial form, that is f of n is equal to the summation k equal to 0 to m of a sub k times the following factorial, then the series f of n by n factorial is equal to e times the series, finite series a sub k. Additionally, we have seen that the series f of n by n factorial is equal to e times a sub naught plus a sub 1, which is equal to e times f of 1. Now, if there is x to the power of n as well, then we would have e to the power of x times the finite series a sub k times x to the power of k. This theorem really helps us in evaluating any series which contains falling factorial. And in the next session, we will look at some examples. So that was polynomial exponential series. Now, if you found this session helpful, please do like, share, and subscribe. Questions, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.